And if anybody's got any questions, I'd be glad to answer them.
I had a question about the advance of the solar cycle. You showed only 3 tracks, and they were a bit ambiguous about angle and rate of attack and how you decide between them. Did you look at other, more historical tracks, and did they spread this out?
Putting all of them on there would really clutter it up. But in general, a faster cycle rises, a big cycle rises faster than a small cycle. And I just tried to show that general concept. You can see that there's a problem in this area right here.
It stays ambiguous for quite a while. And I wasn't sure whether that was typical or distinctive of these 3 tracks. And that's it's what usually happens. And hopefully, like we're about 16, another year it'd be 16 and 12 would be 28. Hopefully things will be separating enough to tell what's going to happen. So we still got to wait.
So I have a quick question, if I may. There's a gentleman named Scott McIntosh who I've heard, and then Tabitha Scove has referred to him as well, and he's predicting a big one. What are your thoughts? Because he's a little bit out on the limb. He's outside that consensus group of 50-some guys you mentioned a minute ago. What are your thoughts on that?
Yeah, Dr. Scott, what he's looking at is he's trying to visualize what's going on with the magnetic fields inside the sun. We don't have any direct measurements of that, so he's inferring that. But it's a good concept because I think it's trying to understand what's going inside the sun. And what his prediction is based on is when a solar cycle ends, and you compare it to the previous ending date of the last solar cycle. And if there's a short interval in between, it's a big cycle. And that's where his big cycle prediction comes from. Initially, he predicted that cycle 24, by his method, would end in April 2020. Well, it did not end in April 2020. It's about, April, May, June, July, August. It's about a year and 5 months past that. And there's no definite end to cycle 24 per his criteria. About a month ago, he and his colleagues revised their prediction down because of just what's happening. So it's not a big cycle. It looks like it might be around an average cycle. Now, what's going to happen as we go forward, I have no idea. Maybe he's going to have to revise it down even farther if the end date per his criteria for cycle 24 is not met yet.
Another question I have is, I think it was at the Dayton Hamvention, there was a gentleman who gave a presentation on using real-time information from like FT8 and maybe Whisper and some of the other digital modes to create a system that would in real time gather information and stir it all up and then help us see where propagation, what current propagation is. I'm curious to know, is there, what do you think about that, and has there been more investment been made in looking at those kinds of modalities to learn more about this?
Yeah, you were probably referring to one of the ham SCI guys giving a presentation.
I don't recall who it was, but I thought it was a fascinating presentation.
Yeah, there's lots of good stuff happening, especially within the ham SCI group. You can go to hamsci.org. I think that's a website. If you want to get involved, do it. W2NAF, Nathaniel Frizzell is kind of the lead guy, and he's a double E professor at the University of Scranton, and he's very oriented towards trying to understand the ionosphere. So that warms lots of hearts of people. But one thing, it's going to tell us how the ionosphere varies in the short term and in the long term and everything. And then we have to tie that data to what's going on with solar flux and K-index and the events that happen in the lower atmosphere. One way we can, our predictions, like I said, they're monthly median predictions. In other words, it's kind of an average look about a month time frame. And of course, what you can do is bring in ionoson data into that model and try and force the model to agree with the ionoson data. And you can do that generally every 15 minutes because, ionosons, the cadence of an ionoson is, there's some that go every 5 minutes, some go every 10 minutes, most of them go every 15 minutes. So you can get a more real-time look with a propagation program doing that. And I know that's going on with, I think I mentioned the International Reference Ionosphere. Right now, the latest version is 2016, and they're working on assimilating ionoson data into their F2 region model to bring it more nearer real time. So that's the alternative to trying to understand what's going on with events in the lower atmosphere and the K-index and the solar flux and all that. But it's a good thing that's happening. And lots of, they have on Thursday evenings, every 2 weeks, they have presentations. So you might want to go to hamsci.org and look at, if you're interested, and see what they're doing.
Hey, Carl, a quick question for you, and I don't know if there's a single answer to this, but can you explain what's behind the whole QSB phenomena that we experience all the time, like we did today, and what some of the factors are that go into the kind of the cyclic, rise and fall of signal that we see at our receivers?
Right. Well, I think the biggest thing we got to remember is the ionosphere varies rather dramatically in the short term. And, the D region undoubtedly is varying. The D region during the day determines absorption. So that could contribute to the signal level. The E region and the F2 region vary. That could impact the MUF. We got the ionosphere varies because of solar radiation, geomagnetic field activity, and events in the lower atmosphere coupling up to the ionosphere. So all those three things cause the ionosphere to vary in very short term. I've read a lot that fading is when there are two different modes, like a high angle mode and low angle mode interfere with each other. I'm not sure I can specifically say that it's this one thing. I think there's just a lot of things. We always think of if propagation exists between point A and B, we say that the MUF is high enough to support the frequency we're on. In other words, the operating frequency is less than the MUF. But we have many observations of when the operating frequency is above the MUF, and there's probably some scatter going on. So all that stuff causes QSB probably. So I don't think I can give you a definite answer. It's a whole bunch of stuff. I think the best thing to say is the ionosphere is varying in the short term, and that's where it all comes from.
Hey, Carl, this is Mike, WA8AH. Thank you for the great presentation. Since radio transmissions basically follow the Great Circle route, and being in the more or less northern latitudes, to say to Asia we typically short path are going to be going through the Aurora phenomena. Can you speak a little bit about Aurora and their effects on multi-skip propagation?
Yeah. The auroral oval is always there. Of course, it has its least impact when the K index is 0 or 1 or 2 or 3. The biggest issue is with the auroral oval is it causes additional absorption when it's very active, when the K index is high, and that's going to kill the path going over the pole. You people in Virginia, to Europe, you don't have to worry too much about the auroral oval. Of course, as you move further west in the States, it gets worse and worse. Again, what causes auroral activity, of course, can affect the F2 region too at the mid latitudes, and that can reduce the F2 maximum usable frequency. So if the F2 MUF doesn't get you, absorption going through the auroral oval could get you too.
This is Roger, KM4LH Zulu. Wondering a little bit about the chemistry. The atmosphere is 80% nitrogen, 78% nitrogen, I think,
right,
and about 20% oxygen. Right. Do they contribute proportionally to ionization? So nitrogen contributes, say, 80% of the ionization?
No.
Okay.
The F2 region is mainly due to atomic oxygen. And it has a ionization. It has a ionization. I have trouble saying that. And what that says is there must be enough energy from the photon to knock that electron off. And it so happens in the F2 region that atomic oxygen is the biggie, and that's about it in the F2 region. As you go down lower into the atmosphere, that's where you start getting into molecular nitrogen and molecular oxygen. And down at D region levels, nitric oxide is probably the major atmospheric constituent that is responsible for the D region. It's and of course the magnitude or the amount of atomic oxygen versus altitude has a lot to do with it too, because it peaks in the F2 region area. And atomic oxygen can be probably very easily compared to some of the others. There's only, when people do production and loss calculations using the chemistry, in general, it's atomic oxygen, molecular nitrogen, molecular oxygen, and nitric oxide. Now, there's a lot of other little things, but they don't contribute especially like atomic oxygen does. Yeah, it's a big chemistry lab up there, especially in the D region, because the D region is very turbulent. There's, all those chemicals are moving around, whereas as you go higher and higher, they're not. So, lots of chemistry going on. There's a question in the chat room from Keith. Oh. Do solar protons and electrons also cause ionization? When there's a really big flare, like an M or X class, that can release very energetic protons. In other words, relativistic And what they do is funnel down magnetic field lines and go into the polar cap, and they can increase D region ionization. So a big solar flare could cause a radio blackout, could cause a solar radiation storm, which is when the over the pole path is degraded, and that's because those protons cause increased D region ionization. Similarly, the protons and electrons the electrons in the solar wind don't directly go into our atmosphere. They get caught in the magnetotail, and when the K index is elevated, I'm not sure we fully understand it, but that's where those trapped electrons can funnel into the auroral zone. And of course, those electrons coming from the magnetotail can cause increased ionization. And one way we see that is with visible aurora, but it also causes radio, I guess you'd call it radio aurora, where our signals have are reduced in strength because of the additional ionization down there because of those electrons that are precipitating into the auroral zone. So, yeah, under certain conditions, protons and electrons from the sun can cause additional ionization. Yes.
Carl, I know there's probably no simple single answer that you can give dummies like me who just want a shortcut. What happens for me is every time I go through one of these presentations, I remember it for about 10 minutes.
Yeah. Yep.
And then I'm like, well, is a high K good or a low K good, or what? So like, if I look at that map on QRZ, which I look at that thing every single day. What are like the 2 or 3 things I should look at that say, all right, maybe we'll have good propagation day, or maybe we won't?
Oh, I think you should look at the solar flux and the sunspot number, and look at the sunspot number and the solar flux, and see where it falls. But you got to remember that it takes the ionosphere a while to build up. To keep it simple. So you got to remember that the sunspot number and the solar flux have to be up at those values for a long time. I mentioned weeks. So that'll give you an idea of what's going on. Again, the easier thing to do is just go look at some of those real-time data sites, websites. And once you look at the sunspot number and the solar flux, then go see what the K index is doing. The K index, the A index, the BZ component, and the solar wind, they all correlate. You want all of them to be low for undisturbed F2 region propagation. So
you want high sunspot numbers, high solar flux, and low K index.
Yeah, that's what HF guys want. Of course, the VHFers want high K index because they get aurora propagation, right? But in general, HF guys want high sunspot numbers and high solar flux and low K indices. But remember, we're trying to simplify some very complicated processes. So, just your mileage may vary.
Oh, I know. Just hearing you talk about it, and it's like part of it's like, all right. So sometimes, like, is this a science, or is this an art, or is this an art and a science, or is this just mythology? That's what I keep.
It's a science, but it's statistical in nature. I think that's what kind of our understanding of the ionosphere is probabilities. And unfortunately, one of these days we may figure out everything and have daily predictions where you enter like a solar flux or a sunspot number, enter the K index for the past, 33 hours, and then you enter some parameter that ties it to those events in the lower atmosphere, coupling up the ionosphere, and it'll spit out what the ionosphere is doing where you want to know what it's doing and at what time. But I think we're pretty far away from that.